This is a collab on policy iteration. So what is policy iteration? It's a dynamic programming algorithm to find the optimal policy for an MDP. So let's go ahead and see what the imports are. We'll import NumPy and matplotlib. So we'll be running the policy iteration algorithm on a grid world. So the grid world that we have is shown before you. There are 16 states. It is a 4x4 grid world. We will be numbering the rows and columns starting from 0. There are two terminal states, 0, 0 and 3, 3. So what are the actions? The actions are north, south, east and west. Each of these 4 actions is possible from every non-terminal state. The reward is equal to -1 for every transition. It stays constant. Even if you transition to a terminal state, the reward is still -1. Regardless of the action taken from any state, the reward is going to be -1. When it comes to actions in the boundary states, if a particular action takes the agent out of the grid world, what the environment will do is it will transition the agent back to the same state from which it started. Or rather, to put it in another way, if an agent tries to take an action that moves it out of the grid world, that action will have no effect on the state of the agent. It will remain in the same state from which it took that action. For example, let's say the agent is in the state 0, 3, this particular state. If it tries to move east, okay, if it chooses the action east, what the environment will do is it will not push the agent out of the grid. Instead, it will keep the agent in the same state, which is 0, 3. Right? So for the state 0, 3, the actions east and north will leave the state of the agent unchanged. All transitions in this grid world are deterministic. Okay, so there is no stochasticity involved as far as the transitions are concerned. Okay, so this is the grid world. One final point about this is that gamma, the discounting factor, the discount factor is equal to 1, and we treat this as an episodic task. Okay, it's not a continuing task, it's an episodic task. So whenever the agent reaches the terminal state, the episode will terminate or end. Okay, so that's the description of the grid world. So once we have the grid world in place, we need to see how we can represent the grid world in code. Okay, let's see how that happens. This is a 4x4 grid world. In general, we could have an m/n grid world. So we use variables m and n to denote the number of rows and columns. The states are represented by tuples. So each state is a row, column tuple. Okay, so there are 16 states. All of them are represented as a list. Okay, a list of tuples, and that is going to be capital S. Actions are these 4 actions, and the list of all actions is represented by capital A. You also need to keep track of the number of actions, so this will come in handy later on. So we use a variable a count for that. And as stated earlier, there are 2 terminal states, 0, 0, 3, 3. Now let's look at how we specify transitions. Okay, so how do we specify transitions? We need to specify two things, right? So if the agent is in state S, takes an action A and moves to the next state S prime, what is the probability of this transition? That is P of S prime given S comma A. We need to specify that. The second thing that we need to specify is what is the reward that the agent can expect starting from state S, taking action A and transitioning to S prime. So we are going to compute 2 quantities. First is P of S prime given S comma A. The next one is the expected immediate reward as a function of SA S prime. Okay. So in the entire collab, whenever we encounter the next state or the next value function, we'll use this next, we'll append this next to the variable name, right? So S will represent the current state, S underscore next will represent the next state. Likewise, V will represent the value function of the current time step, V underscore next will represent the value function for the next time step, right? So this is how we will be using this phrase, this term next, right? That will be used to indicate that we are talking about the next state or the next time step. Okay, coming back to the transitions, if the agent is in state S, okay, state S is what? Some row comma column. We have to determine what is the effect of an action on the state, okay, or rather on the agent, right? What is the effect that an action will have if the agent is in a particular state? So if the agent is in state S and it takes the action north, two possibilities could be there, right? So if it is a border state, then the agent will remain where it is, okay. If it is not a border state, then the agent will move up, okay. So this is not true for every border state, right? So for example, 3 comma 1 is also a border state. Now the agent can move up, right? Or if it tries to move up, it will end up moving up, right? Or if it tries to move north, it will move north. So this is not true for every border state. So there are some border states for which the agent cannot move north, or it has the agency to move north, but then the environment will step in and say, no, I won't allow you to move outside the grid. I will put you back in the same state from which you started. So when does that happen? It happens when R double equal to 0 in this case, right? So if the row is 0 and the agent tries to move north, row will remain 0. This is what this means, right? So R is equal to R if R double equal to 0, else the agent can move north, or the agent will end up moving north, okay? So if the agent moves north, what effect does it have on the row? The row should decrement, or the row should decrease by 1. Okay, moving up means, moving north means the row decreases by 1. Moving to the south means row increases by 1. That is what the A double equal to south means here, right? R plus 1. West and east likewise, the column decrements by 1 if you move west. The column increments by 1 if you move right. Again, there are border states that you have to be aware of, right? So if you are on the border and if you try to move outside the grid, you are allowed to take that action west. As an agent, you have agency, right? That's what agent, the whole idea of the agent means, right? Agent has complete control over what actions to choose. Okay, agent has complete control over what actions to choose, but then it has no control over where it will end up in, because that is under the control of the environment, right? So the agent can decide to move whichever way it wants to, that is under its control, but then finally it is the environment's call as to where it will land, okay? So that is captured by this transition probability P of S prime given S comma A, right? So that is finally under the environment's control. Okay, so that is regarding the transition. So once you transition to the new R comma C, please note that we are reusing R comma C. So at the end of these, the whole sequence of if statements, what will happen is R comma C will hold the new state that the agent has moved to. Okay, it could end up being the same state that it started off with, but that is immaterial for us, right? So R comma C is the new state that the agent has moved to. Now what are we trying to compute? P of S prime given S comma A, right? Since the transitions are deterministic, if the new state that the agent has moved to is equal to the S prime, S next mind you is S prime, then give all the probability to that particular S prime, right? So P of S prime given S comma A equal to 1 if S prime happens to be the new R comma C that we have computed. If not, 0, right? For all other transitions, give 0, right? So this is a typical way to encode a deterministic transition. We have a constant reward for all time steps, so this is not going to change. Okay, finally you return the probability, the transition probability, and the expected immediate reward when you take an action A from state S and you transition to S prime. Okay, so this is all about transitions. So once we have defined the transitions and overall makeup of the grid world, our environment dynamics is established. So what do we need to do next? We need to find a way to define policies. Okay, policy is what? How to behave, right? How the agent behaves is encoded in its policy. So we will start with what we call an equiprobable random policy. What do we mean by that? An equiprobable random policy is a random policy, but then each action is equally likely, hence equiprobable. In this particular case, if the agent is in a state S, each of the actions can be taken with a equal probability. Since there are 4 actions, the probability will be 0.25 for each action. Okay, so pi of A given us is equal to 0.25 for all A and for every S in the state space. Okay, this is the policy that we would like to define. How do we define it? This is how we are going to define it, right? So pi is a dictionary of dictionaries. Okay, the outer key is going to be the state. The inner dictionaries keys are going to be the actions. Okay, so this is actually 0.25, right? So each one is 0.25. So forget what I've written here. This should actually be as simple as this, right? So pi of SA equal to 0.25 for all states and actions, right? So let me just demonstrate this for, let's say, the state 0, 2 and action being east. Okay, let's run this. You will end up getting 0.25. So if you want to visualize or picture the entire thing, this is how it will look, right? So notice that each key is a state and you have a dictionary that captures the actions and their corresponding probabilities of being taken in that particular state. Okay, so this is the policy pi. This is how we are going to define policies. Okay, now we start looking at the algorithm policy iteration. Let me remind you, it has 2 parts to it. One is policy evaluation and the other is policy improvement. Okay, first we will look at policy evaluation. So there are 2 kinds of updates possible. One is synchronous. In a synchronous update, we maintain 2 copies of the value function. In the in place version, we maintain only 1 copy of the value function. Okay, so the update rule is as follows for policy evaluation, right? Now we can also write this down as the one that I have written down here, right? Where instead of using the joint probability over the next state and reward, we are splitting it into the transition probabilities and the reward expectations, right? Because this is what we have actually written the code for, right? If you remember, we are computing 2 things in our transition function. We are computing 2 things, right? One is the P of S prime given S comma A, and other one is the expected immediate reward as a function of SA S prime, right? That is exactly what the second formulation is, right? Transition probability, reward expectation, both as a function of SA S prime. Okay, so we'll use the second version of the update. So let us go ahead and look at both the synchronous and the in-place versions of policy evaluation. So we'll look at the synchronous version first. First, let us study what these first 9 lines of code are. Okay, first 9 lines of code. So this determines convergence, right? This talks about convergence or the variables that are important for determining if the algorithm iterative process has converged or not. Okay, so what is delta? First, let's look at delta. Delta is the difference between the value functions of successive iterations, right? So if vk is the value function for time step k and vk plus 1 is the value function for time step k plus 1, then delta is going to be the difference between vk and vk plus 1. So remember that both vk and vk plus 1 are vectors or functions, right? So what do we mean by the difference? So you compute vk plus 1 of s minus vk of s, the absolute value of this for all possible states, okay, and take the max over this. Okay, so that will be delta. Okay, you do vk plus 1 of s minus vk of s for all s. You'll get, there are like 16 states here, you'll get 16 values. Take the maximum among these values, right? So when we say difference, it's the absolute value of vk plus 1 of s minus vk of s. So that is delta. Delta captures the difference between two value functions, or how close they are. Now if this difference, right, ideally it should keep getting smaller and smaller. The moment it becomes small enough, we say that policy evaluation algorithm has converged, right? So how small should it become? That is specified by this variable theta. So theta is going to control how close you want to go to your, or how close you want consecutive iterations to be, right, or the consecutive value functions to be. So if you want a very small difference, theta will be say 1 e power minus 7 or something like that, right? So currently we are setting it to 10 power minus 3. So once you have defined the variables that are required to ensure convergence, you move on to defining the value function, right? The variable that will keep track of the value function. We call that simply as v, and v is going to be set to 0 for all s. Okay, so it's a simple dictionary. For each state s in capital S, set the value to be 0 to begin with. Okay, this is your, you can think about this as v subscript 0 or time step 0. This is the value of all the states. So iter is nothing but a variable to keep track of the number of iterations. We want to see how many iterations it takes for the algorithm to converge. So now we come to the actual loop, okay, actual algorithm. Let's go line by line. So when do you converge? You converge when delta becomes small enough, when delta is less than theta. So that is when you converge. Therefore, you have to keep running the loop as long as delta is greater than or equal to theta. Okay, that is the loop condition. Now, since it's a synchronous update, what we'll do is v next, we'll also have a vk plus 1, right? So vk is this v, vk is v, vk plus 1 is going to be v next. Okay, that is also initialized to 0. Okay, notice this part, v next is initialized to 0 at the beginning of every iteration. Okay, that's important to notice. Now the maximum difference in the values, right, delta, is set to 0 again at the beginning of every iteration of policy evaluation. Now focus on these lines. What are we trying to do? We need to update the value of vk plus 1 of s, which is v next of s. So this is what we have to arrive at. How do we update v next of s? For every state s in capital S, okay, we first check if s is a terminal state or not. According to the algorithm, if you remember, if it's a terminal state, its value should not be disturbed. Okay, why is this the case? If you are in the terminal state, your episode has ended, right? So there is no point in taking any actions from that state. The expected return starting from the terminal state and behaving according to the policy pi is 0, right? So there's no return. So if s is in the terminal state, you continue, meaning you don't update v next of s. And this, since v next of s is initialized to 0, the value of a terminal state will remain 0. Okay. Now for all non-terminal states, what should you do? You have to behave according to policy pi, right? You have to behave according to policy pi and compute the expectation. Okay, you have to compute the expectation. Now, what is that? So this is the formula that we have to use for the update, right? So you have to go through all actions A in state S, compute pi of A given S, and then you have to look at all possible next state and reward combinations. So there is a small change that we have to do here. Please make this correction. This should be the summation is over only the next states, right? It's not over the rewards. Why is that? The summation is only over the next state. The reward is already captured here, right? So that goes into the reward expectation, right? So R of SAS prime, remember, is the expected immediate reward. So that summation over R would have already been captured in R of SAS prime. Okay, so please make this correction. In few minutes back, I was actually showing you summation over S prime comma R, but here the summation should only be over S prime. Okay. So let's go back. So what do we need to do? We need to do this. We need to carry out this update. So what we'll do is we'll first look at one action, one next state, and see what happens, right? So one action, one next state. What do we need to do? We need to compute the probability of the transition and the expected immediate reward as a function of SA S prime. That is what this transition function is giving us. Once you compute that, what does the update rule say? It says pi of A given S into that probability into the expected immediate reward plus gamma times Vk of S prime, right? Vk of S prime is what? Vk is V, S prime is S next. Okay, so Vk plus 1 is on the left. Okay, why are we doing this plus equal to? That is because what we have done is for a single tuple S prime. But what we have in the update rule is a summation, right? We have sigma over A and then sigma over S prime. That's why we have these two for loops, right? For every A in capital A and for every S prime in S, compute this quantity. Okay, compute this quantity, keep adding it to V next of S. Okay, to begin with, V next of S is anyway 0. Okay, so it's okay. We can keep adding it. No harm there. Finally, once you come out of this for loop, what you will have is V next of S. You would have computed V next of S. Okay, all this is for one state. Now repeat the whole process for every possible state that is there in the state space. And once you come out of this for loop in line number 30, 31, you would have computed Vk plus 1 of S completely for all S. And once that is there, make that the new value function, right? So we have to update V. So V next is now the new V. Why is this needed? Because when you go into the next iteration, you will be using V, right? You will be using V as the current value function. So you need to update the current value function to the new one that you have computed. And you do this V next dot copy because you don't want to end up updating the same object. So you create a copy of this object V next and save that in V. Okay, so finally what we do is we just round off the value function and then we print it. Let's see what happens. Okay, so I'm sorry. So this is a helper function that will convert the dictionary to numpy object. So that's what this toNumpy is. It will take a value function dictionary as input and it will convert it to a numpy array. So now that the helper function is defined, we notice that it takes 131 iterations for policy evaluation to converge, and this is the value that it converges to. Okay, so the terminal states are 0, 0. This particular state has a value of minus 14, this is minus 20, so on. These are what? These are the values of the states if the agent acts according to this policy pi that is given here. This equiprobable random policy, if the agent behaves according to this policy pi, this will be the value. Okay, so what we have done is we have computed the value function corresponding to this policy pi using policy evaluation, but synchronous manner, in a synchronous manner. Now we look at policy evaluation with the in-place version. Okay, in-place version, lot of things will remain the same. So I'm not going to go over the threshold for convergence and the initialization of the value function. Okay, so the convergence condition is still the same. So the loop condition is also the same. Initialization of delta, all this is same. The only difference is we don't have a V next. We have only one copy of the value function V. Okay, notice that there is no V next being initialized as 0, right? So we have only V. So we still sweep through the state space. Okay, one thing that I forgot to mention earlier was when you go through all the states, okay, each and every state once, you call that one sweep through the state space, right? So we are going to do one sweep over the state space. And the new value, right, we'll be computing the new value for the state S. We'll call that Vs. Initially Vs will be 0. Terminal states still are not going to be updated, so that part of the code also remains the same. Now we have to compute this update, right? What is the update we have to compute? So we have to compute this update, and we have to go over each action and each next state. So we do that. This is the probability and the reward for the transition. Okay, so the transition probability and the expected immediate reward as a function of SA S prime, all that remains the same. Okay, so you keep adding this to VS. Okay, nothing, all this remains the same. Finally, you update delta. So this is the new value of the state. This is the old value of the state. You update delta and you update V of S. Okay, finally you update V of S to be this new VS. So why is this an in place version? Because you are using only one copy of the value function. So for some states, or rather for every state, what will happen is some parts of the value function you'll be using the old value function or the current value function. Like let's call it current and next, right? So for some updates or for some states you'll be using the current value function. For some states you'll be using the newly computed value function, right? So for some states you'll be using the current value of the value function itself, but for some other states you'll be using the just most recently updated value. Okay, so that is the in place version. So let's again run this and see. Same policy, equiprobable random policy. Now notice the difference between the two. Both of them converge to the same values. So the value function v pi of s is the same. Here it's 0, minus 14, minus 20, so on. Here also it's 0, minus 14, minus 20, so on. But the difference is the synchronous version took 131 iterations for convergence. The in-place version took only 88 iterations. Okay, why do you think this is the case? One possible explanation is that the in-place version, right? In the in-place version, we tend to use the newly computed value function for certain states, right? So we tend to use the newly computed value function for certain states. So in some sense, they are more recent, correct? So in some sense, these updated states, when we use these values, they are more recent or more accurate than using the old values for all the states. So in the synchronous version, what do we use? What do we do? We use the old value for all the states, right? We use vk of s prime only for all the states, whereas in the case of the in-place version, for some of the states, we end up using the updated versions of the values, right? I'm not sure if I have made enough sense here, but I hope you see that this in-place version is going to converge in fewer iterations because it is using updated values for many states. Okay, it doesn't wait for one full sweep to end before taking or making use of the newly computed values. Okay, so that is one potential explanation for why it takes fewer iterations for convergence. Once that is done, we have policy evaluation in place. So one final point regarding policy evaluation is this. So what we have done is we have turned this into a function. Okay, if you input the policy pi, that is going to evaluate the policy pi and it is going to return the value corresponding to that policy and the number of iterations it took. Okay, so that makes it a little more modular. Let's now go to policy improvement. So how do you improve the policy? If you have a current policy pi and you have already computed v pi for that policy, if you want to get a better policy pi prime, you can do that by being greedy with respect to v pi. Okay, this is what the policy improvement theorem guarantees for us. If we behave greedily with respect to the value function for the current policy, you will end up with a better policy than the current policy. That's what policy improvement theorem guarantees. So let's go ahead and define our new policy to be pi next. This is what we need to compute. Okay, so for every state and every action in that state, we set pi prime, right? Pi next is what? Pi prime. Pi prime of a given s to be 0. This is actually incorrect, right? Because probabilities should sum to 1 for every state. they do not sum to 1 here, but that's okay, because we will update it, right? This is a, we are doing this for convenience, right? Finally, when we return pi next, it will be a valid policy. Okay, so how do we update it? So how do we compute pi prime? By being greedy with respect to v pi. Okay, so what does it mean to say that we are greedy with respect to v pi? For each state S, choose that action which will have the maximum action value q pi of s comma a. I'll repeat this. For each state S, choose that a for which q pi of s comma a will be maximum. So it's good if we can compute the q values or the action values. So that's what we'll do next. So we'll compute the q values. So q values can be defined as a nested dictionary, right? For each state S, you define a dictionary of actions, a dictionary of action value pairs. So for each a, initially the q value is set to 0. So how do you update this? For S in capital S and for action A in that state, and for S prime in S, you again do the same thing. You compute the transition probabilities and reward expectations. Okay, now instead of finding v pi of S, we are finding q pi of S comma A. Therefore, this pi of A given S business will not be there. You'll only have sigma over S prime P of S prime given S comma A into R of SA S prime plus gamma V of S prime. Okay, that's what this is. Only difference between this and v pi of S is that sigma pi of A given S over A is not going to be there, because this is the action value. So once you compute the action value for all actions in a given state S using this inner for loop, what you need to do is find the maximizing action, okay, or find the action which has the maximum q value for that particular state. This piece of code does just that. Okay, I'm not going to go into more detail about how this line works. I leave you to figure that out. It's just an R max over q pi of S comma A over all A. Okay, that gives you A max, the maximizing action. So what do you do next? Once you have this best action in status, you make that the action to choose, right? So we are computing pi prime, and that's a deterministic policy, right? Therefore, once you have found the best action from the status, make pi of A given as equal to 1 for that action. And since we have initialized pi of A given as to be 0 for all state action combinations, this will end up working for you, right? So you'll have 1 only for the maximizing action. Okay, you'll have 0 for everything else. So this will finally end up being a proper probability distribution. Okay. Now one question you might ask, and you should ask at this stage, is how are we breaking ties when it comes to multiple actions having the same maximum action value? So this is important. We have to break ties consistently, right? In policy improvement step of policy iteration, we have to break ties consistently if we want our policy to finally converge, right? We need to, what is convergence in policy iteration? You have a stable policy, right? That is when we know that it has converged. So for that, we need to break ties in the maximum valued actions consistently. We are actually ensuring that here. Okay, so we are looping through A in capital A. So, and this tuple that is created is actually ordered from left to right. So whatever is the order of actions in A, that's the corresponding order will be followed in this list. Okay, so the ties will be broken consistently here. Okay, I will again leave you to verify that this is the case. Okay, once you have found out pi prime, you return pi prime. Okay, so this is what happens. Let me just run this for current policy and value function v pi. You'll end up getting pi next, right? You can visualize what pi next is. Let me run this again. So it is some deterministic policy, right? So some deterministic policy. This is how it looks. Okay, now we move to policy iteration. So what is policy iteration? You keep doing policy evaluation, and then you keep improving that policy, and then you go back again and evaluate the value function for that policy, improve that policy by being greedy with respect to the value function. You keep doing this until the policy stabilizes. Okay, so what we have here is pi prime and pi. Okay, we'll be checking for stability here. While pi prime and pi are not equal, do one more round of policy iteration. Okay, so I'm not going to look too much into what pi and pi prime are to begin with. Okay, so that I leave you to figure that out as well. So while the policy has not stabilized, okay, look at the current policy. So you're doing this, you're copying the previously computed policy and making it pi. Okay, you are evaluating pi, or rather you're finding out the value function v pi for this policy pi. You're calling that v. Okay, you're being greedy with respect to v pi. That gives you pi prime. That gives you pi prime, and then you go back. You have computed. So you had pi, some pi to begin with, and then you computed pi prime. So you'll have to check if pi is equal to pi prime or not. If they are not equal, do one more round, right? Now make pi prime the new pi, compute v pi, improve upon this pi by getting pi prime, keep doing this until, okay, this, so this converges, right? This, the policy stabilizes. So whenever pi becomes pi prime, that means that the policy has stabilized. You can come out and print that particular policy, okay, or the value function corresponding to that policy. So let us run this. We see that policy iteration in this case converges after 3 iterations, and this is the optimal value function for this policy. If you think about it intuitively, it makes sense, right? So these are terminal states. What is the optimal value starting from this state? It is -1. Okay, what does that mean? It means that if you follow this optimal policy, whatever it is, it will take you, it will give you an expected return of -1. Okay, now if you change all the negative signs to positive signs, what this actually gives you is the number of steps that you need to take until you reach the terminal state, or number of steps that will take you to the terminal state. So for example, here just one step to the left will take you to the terminal state. So if you are here, 2 steps are needed, right? 1, 2. Okay, and this is when you are behaving optimally, right? Of course, you could go in a roundabout way. You could go down, 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 up, up, left, right, up, 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 right? So let me repeat that: down, down, left, up, 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 right? So that will take maybe, I don't know, 1, 2, 3, 4, 5, 6, right? 6 steps. Okay, that has a return of -6, right? But that's not an optimal behavior, right? So the expected return starting from this particular state and behaving optimally is -2. Or in other words, we can say that it takes 2 steps if you follow the optimal policy to reach the terminal state, or one of the terminal states, right? In this case, the nearest terminal state is this, so it's going to be 2. Okay, for something like this, interesting thing we'll see in the next piece of code is that the return is expected return is -3 if you behave according to the optimal policy. So you could go 1, 2, 3, or you could go 1, 2, 3, right? Both these terminal states are equidistant from the state. So we'll see how that shows up in the optimal policies that we have. Okay, that's policy iteration. Now let's look at optimal policies. Now remember that for every finite MDP, you will have at least one deterministic optimal policy. That is for sure. Now you could also have stochastic policies. So what we'll do now is we'll try to find out all possible optimal policies for this problem. How do we find that? We have V star with us. We have the optimal value function V star with us. So we'll again look at a greedy behavior with respect to V star. Right? To find all optimal policies, we look at all possible actions that will give us the maximum value of Q star of S comma A. Right? Q star of S comma A is the optimal action value function, right? So that's what we'll compute, and we'll find out all actions which have maximum Q star for state S, right? That's what we'll do. So Q is set to 0 to begin with. So for S in S, and if S is terminal, again, don't worry. If A is So for each A, for each S prime, you get the transition probabilities and reward expectations, and you compute its Q value, right? The only difference here is that we are now computing the optimal Q values, right? So these are what? These are the optimal action values that we are computing, right? So we are computing the optimal action values. Once you have computed the optimal values, that is Q star of S comma A for all A in a given S, we are now going to find all optimal actions for the state that is going to be stored in optimal actions, right? So how do you do that? First you find that action, or the maximum value for the status, so that is max Q. Okay, max Q, that's the maximum value for the best possible action, and you see what all actions A for A in capital A, if QSA equal to max Q, right? You look at what all actions have this maximizing value. Okay, all these actions are optimal in the status, and therefore we call them optimal actions. Okay, so what the rest of the code is doing is, it is just going ahead and plotting the actions on the grid world. Okay, using arrows. Using arrows, it's plotting these actions, and this is what we have here is just some code for matplotlib to plot these properly, right? This set of code is also the same. What we are interested now is in the output that we get. So we are printing two things. One is the optimal action. The other one is the V star of S. Okay. So V star of S we have already seen, it's -1, -2, -3, right? If you remember, this is what was displayed here. Okay, so that is being mentioned here in the bottom left, and in each cell you see the maximizing action or the optimal action. So in some states we have multiple optimal actions, right? So what you could then do is you could define deterministic policies there, or more natural thing that you can think of is you can convert each of these into a valid action and give some non-zero probability to it. So for example, I can define the policy for this state to be 0.5 if you go west and 0.5 if you go north. Okay, right? So that is a valid optimal policy, right? For what I mean is I can give non-zero probabilities to all optimal actions and zero probabilities to all suboptimal actions, right? So I could even give 0.7 if you go left and 0.3 if you go right. All that we care about is for the optimal actions, the probability should be non-zero, and it should be 0 for all non-optimal or suboptimal actions. So in this plot, we have not specified what the suboptimal actions are, right? We have only specified what the optimal actions are. So these two states that you see here, which have a value, optimal value of -3, they're interesting because every action that you can think of is optimal, right? So you can give any probability that you wish for any of these four actions. As long as they sum to 1, you are good. Okay, so this gives you a complete specification of all optimal policies for this particular grid world task. Okay, so what maybe we'll do is we'll just go ahead and look at a slightly different grid world where we turn this into a normal non-terminal state and we have only one terminal state. Let's see what happens. Okay, we'll stop with that. So I'll just go ahead and remove this as a terminal state. Okay, what happens if we remove 0, 0 as a terminal state? We can now run the whole collab and see what happens. Okay, notice what happens. This is no longer a terminal state, and then so the optimal policy is slightly different, right? So for example, if you start from here, the V star of this particular state is -6, which means it takes 6 steps to reach the terminal state, right? Let's count 1, 2, 3, 4, 5, 6, right? So very nice looking plot. Okay, so I encourage you to write the entire piece of code on your own and try out various possible configurations of the grid world and see how the value function behaves, right? or the computed optimal value function, how does it look like. Okay, so let's just go back to the old configuration. Okay, so that ends the collab on policy iteration. Thank you for watching.